So for the further study, we need the applications of vector cross product, which I introduced to you while I was teaching vectors. Along with vector dot product, I told you about the vector cross product. That's why I'm writing a revisit. Okay, and this is defined mathematically as A cross B is equal to a vector C. A cross B is equal to a vector C, and this is a new vector, and this is a way of obtaining a vector from two vectors which are already defined. A vector can be defined all by itself, or if a vector is multiplied by a scalar. I've told you about that, we have discussed that. So A cross B is equal to vector C, the new vector, such that the vector C dot A or C dot B or A dot C or B dot C is equal to 0. Because in dot product we obtain a vector here. If I have a dot product, then I have a scalar over here, which is equal to AB cos of theta. So because now this vector C is perpendicular to both these vectors A and B. If the vector C is perpendicular to both the vectors A and C, there is only one situation which is possible, okay, and that is the vector C should be normal or perpendicular to the plane which contains the vectors A and B, as I told you before. So in this case I am just drawing vector A over here and vector B over here, and translating this vector A from here to here and translating the vector B from here to here. Okay, what I find is that we have a parallelogram. We find that the magnitude of this vector C, or the magnitude of the cross product of the two vectors, is equal to AB sine theta, which is the area of the parallelogram made by the vectors A and B. In this case, I tell you, and I've shown it here, that the direction vector or the unit vector C cap is perpendicular to the plane containing A and B. Containing spelling is a mistake. Containing, okay, so please make this amendment, is perpendicular to the plane. Now how come this can be perpendicular to the plane? The plane is the board here, and if you are writing in a copy, then the plane will be like this on your copy, and the perpendicular directions to this plane are two. One which is out of the board, sorry, this will be better, out of the board in this direction towards you, and the other is into the board, which is going in the opposite direction. In this case you can see that this is the angle theta is a positive angle, and B sine of theta is like this. So A, the magnitude here, multiplied by B sine of theta, that will give you a rectangle over here, and that is the area of the parallelogram. So C cap is out of the board in this case. But here I have taken the same string A and B, the two vectors, wherein this angle is, the B is making an angle which I can say is minus theta by the definition of the angle. And we find that the area, again, it makes a parallelogram by shifting B here and A here and getting a parallelogram over here. So similarly I get parallelogram, the area of the parallelogram is given as AB sine of theta. I told you on that day that how come we can obtain the direction of this vector? It's easy with your right hand. The right hand and the curl of the fingers. If I take this vector like this, okay, and keep my thumb outstretched, then you can see that the thumb is coming out of the board. Okay, so that gives the direction of the C cap, or the unit vector, or direction of C, which is the product vector of the cross product here. And in this case, look here, if I am going to rotate the first vector in the string of A cross B towards the second vector, then you can see now my thumb, outstretched thumb of the right hand, it points inside, and therefore we say that the C cap is into the board. Now what I can get is, this is the right hand curl rule that I am telling you. There is a screw rule also. If you want, you can subscribe to that, but I think that the right hand screw rule is okay. Now A cross B is equal to minus B cross A, just because the two directions of C cap are opposite to each other. The product, the magnitude of these two, A cross B, and the magnitude of B cross A are equal, because in both the cases the area is the same. Also, in reflection, what happens in reflection? In reflection, this vector A becomes minus A and vector B becomes minus B. All the components of the vector, they get just opposite to each other in the process of reflection. So I can write A cross B will be equal to minus A cross minus B. And of course it means that it is again, if I take the minus out and the minus out, and minus multiplied by minus is equal to plus. So you can say that this is nothing but plus A cross B, and the two are equal to each other. This is another thing which we got to emphasize. One of the things, this I also emphasized before, that A cross B1 plus minus B2 is equal to A cross B1 plus minus A cross B2, which means that the cross product has a distributive law associated with it. That is also true for the dot product, and similar things are written over there. But one thing is there. In most of the texts, you will find that they write this equation as A cross B plus C. And this is, of course, then A cross B plus A cross C. But I am taking it as B1 and B2. Why? Because I got to emphasize to you that this vector and this vector got to be from the same family. Okay? Velocity, velocity, acceleration, acceleration, force, force, momentum, momentum, etc., etc. So only quantities, vectors of the same variety can be added, any number of B1, B2, Bn, plus or minus, whatever you want to say in the resolution of those vectors. So this is a single vector of a single variety. Of course, in the cross product A cross B, we can have the two vectors A and B of the same kind, velocity, velocity, acceleration, acceleration, etc. Or we can have one of the vectors as R, the other P, R and F. Okay, we'll use that R cross P, R cross F, etc. in the due course of time. Now one more result I want to introduce to you, that A cross A is equal to 0 because the angle theta is equal to 0, and then sine of 0 is equal to 0. Also A cross minus A, that is also equal to 0 because the angle is 180 degrees, and the sine of 180 degrees is also equal like the sine of 0 degrees. Okay. So after that, now a vector in the rectangular coordinate system, or what we call the orthogonal coordinate system, where there are three axes x, y and z, there we define vectors I cap, j cap and k cap. These are unit vectors, they don't change, okay, they are kind of constant, and I can write this vector A as ax I cap plus ay j cap plus az k cap, where ax, ay, az are the components along the x, y and z axes. So what is important now, that I write for you that like this, A cross A is equal to 0. I can write I cross I is equal to 0, j cross j is also equal to 0, k cross k is also equal to 0 because theta is equal to 0. But then let us see, taking the cyclic order I, j and k, in that cyclic order, I cross j is equal to k cap, j cross k is equal to I cap, and k cross I cap is equal to j cap, and in all these cases the angles between I and j, j and k, k and I are 90 degrees. I have done it before. Then I am writing it with different in that I change the order. J cross I will be equal to minus k because of this property, that A cross B is equal to minus B cross A. K cross J is equal to minus I, and I cross K is equal to minus J, because you can also think that the angle theta that is made over there is minus 90 degrees, and sine of minus 90 degrees is equal to minus 1. So the next item is, if I have two vectors, A is given as ax I cap plus ay j cap plus az k cap, and similarly I can write here b, bx, by, bz. Then I will just tell you how the vector can be, A cross B can be evaluated. So now let us take an example. And this example I am taking a position vector R, and I take the components along the x, y and z axes, rx, ry, rz, that we have been doing before also. And then there is a force vector which has components fx, fy, fz, and that is expressed in newtons. Of course, I, j, k, etc. Now, one of the methods of solving a cross B kind of problem, the cross product of the two vectors, is to write a determinant in this form. On the first row I have I cap, j cap, k cap, then the components of the first vector rx, ry, rz, and then the components of the second vector along the x, y and z directions, fx, fy, fz. Now when I split it, I can write this determinant 3 by 3 into components. In the first one, I forget about this I, the first column. Only the second columns have ry, rz, fy, fz. And in this case, in the second case, which is associated with j cap, I write it as Rx, Rz, Fx, Fz, like here, and for the third part is K, cap, and then this is gone, and then I have Rx, Ry, Fx, F, Y, which I write over here. Now you know, and you must know, you ought to know that if I want to write this as component, then I will write this into this minus this into this. This into this minus this into this. This into this minus this into this, which I have written over here. So the I, J and K components are written like this. Okay. Right now they are Rx, Ry, Rz. They could be 1, 2, 3, minus 1, 2 and 5, like that. When the numbers are there, then it is easy for us to make the calculations and find out the value. So, because this is the value of R cross F, then let us find the magnitude of R cross F, which will turn out to be equal to this number 1 whole square plus this whole square plus this whole square, and this is the value of the square of R cross F, which is the magnitude of the resultant vector. So I can write, I have just briefly written it here, just like that, this plus this whole square under root. Where R is, I can calculate the value of R also, I can calculate the value of F also from these coefficients for I, J, K, that we have Rx square plus Ry square plus Rz square. This is a regular thing that we have been doing even in the case of dot product, and F is equal to Fx square plus Fy square plus Fz square. The unit of this vector is meters, and the unit of this vector is newtons. So the unit of the product vector, the cross product vector, turns out to be equal to Newton, meter Newton. Okay, which is the same. Look here, which is the same as the unit of work, but we don't write it like that. We just call it meter Newton. Okay, so this is about the cross product and how to determine the cross product. I could have taken here, I could have taken the vector P, Px, Py, Pz, Fx, Px, Py, Pz, and here Py, Pz, Px, Pz, Px, Py, etc. and similar result I could obtain, and R cross P is another very milestone kind of a thing. Okay, and I'm going to introduce that to you shortly. R cross P and R cross F, these are the two vectors which are useful here, and we'll also see that there are angular velocities and accelerations, etc. There is a cross product there also, which we can determine. Always remember, before I close that if there are two vectors string A, like this, and B like this, then we have to use the right palm and the fingers, they curl like this. And when I take the first vector toward the second vector, then my outstretched thumb gives the direction of the product vector. If I come like this, okay, then my thumb is inside, so the cap vector or the vector itself, which is the product vector, will be into the board, and for which if
you have forgotten, just to remind you that this is the symbol of an arrowhead coming out of it, and this is the rear of the arrow going away from us into the boat. Okay, so this is it. One day I asked you to give me a page of paper, and I told you you cannot, because for a paper that we have, for a couple of surfaces that we have together, because it is not a page of but two pages which we call a leaf, this side will have a vector in this direction, surface vector, and on my side the surface vector like this.
So after the discourse on the vector cross product, which we'll be using shortly, here I'm going to introduce to you for the rotational motion system of particles. I'll just take up a case of a rigid body. A rigid body which has been shown over here like this. This is spread in 3 dimensions, and I take the center of the coordinates over here, and like before when I was saying that this is x-axis and this is the y-axis and this is the z-axis, but here I have taken in this case this axis as the x-axis, this one as the y-axis, and this axis as the z-axis. Of course, the cyclic order has been taken into consideration. Okay, the cyclic order is the same. Now what happens is that we choose the axis of rotation as the z-axis, and then it moves around as has been shown by this circular kind of a indication over here, that it will move like this in the about the z-axis. This is a fixed axis. It could be the same kind of a motion could be done along the x-axis, along the y-axis, etc. But right now we have confined our axis to the z-axis for this body of an irregular shape. It could be of a regular shape also. We could choose the point of the axis, the orthogonal axis, and we can choose the axis as we desire. Now here, all points on this axis, on this body, when they are rotating, then they will go round in a circle. The path that I have shown is a bit confusing by drawing a spool here, and suppose there is point P. At a time t, after this rotation, and it has got a velocity v which has been shown over here, and of course this velocity will be perpendicular to the radius here, and it will be as has been shown over here. This will be the velocity vector, which is the linear velocity associated with this point P, and this is tangential to the circle at this point. This circle represents, I've just taken any circle, and of course this is this point. If I call it the C here, then this point again is the C. Okay, so all points on this rigid body will undergo a circular motion, and the angle that is traversed in a time delta t is taken as delta theta. I can take this t any value, I can take this value as equal to 0. So when I find
this kind of description, then we learn about the angular velocity and its relation with the linear velocity. It's a very simple thing. The delta theta in this case of circular motion, I have shown it before also, and we have discussed that this is directly proportional to the time which has been spent. So on the average, delta theta will be proportional to delta t, and the requirements of the proportionality, a direct proportionality, a linear relation between delta theta and delta t, is that there should be a constant of proportionality. The constant of proportionality over here is taken as omega, and I can write this omega as delta theta upon delta t, which in the limiting case, the delta t tends to 0, this becomes equal to d theta upon dt. Of course, theta is in radians and this is in seconds, so it will be, the unit will be, as I have told you before, the unit associated with omega will be radians per second. We also found in that case, in a circular motion case, that the velocity associated with this particle p at this instant of time, that is the instantaneous velocity, will be equal to omega into r, where r is the radius of the circle in which it is traversing the circle. So we now just understand in this introduction that omega, which is the angular velocity associated with system of rotation, which is defined as d theta over dt, this is true for all particles, because all particles are moving in their circles with a constant angular velocity. And we find that the associated with all particles I, they may be particle 1, 2, 3, 4, n, associated with that is given by Vi is equal to omega Ri. And we see that this Vi is a function of omega and also the value of r. So it will depend upon the value of r and it will depend upon the value of omega. So this is how the things are taking place here with that introduction, and naturally, like all kinds of motions, then I have differentiated my theta over here, d theta over dt, and I have got the angular velocity omega. If I differentiate it again, d2 theta upon dt2, then I will get it as d omega upon dt, and we have a measure of an associated acceleration, which I am going to discuss in details with you in the next lecture. So again, I emphasize about you question and we answer in the comment section if you have any difficulty understanding anything. Okay, and of course I'm not good at that, but you must draw this proper diagram. It is not a circle, but it is in this plane, in the plane which is perpendicular to the z-axis. I have this, and in this plane I have this particle p, which is rotating, reaches the position p dash, and all of them are, all particles on this circle are at a distance of r from this, what I have just suggested to be the center on the z axis or any axis of rotation associated with this rigid body. So thank you very much for the day, and I wish to take up your questions. I desire that you send me your questions, even if they are of numerical nature, or where wit is required to answer the question in a very short time, like in the MCQs, multiple choice questions. So thank you very much again, and we meet soon.